Chapter 2.2, Square root of a function. The function y equals the square root of f of x is the square root of the function y equals f of x. The restrictions for y equals the square root of f of x are defined for f of x is greater than or equal to 0 because you can't take the square root of a negative number. So if we're putting f of x under the square root, like we are here, then f of x would have to be greater than or equal to 0 for square root of f of x to be defined. Compare y equals f of x and y equals the square root of f of x for a linear function. Given f of x equals x minus 2, write an equation in terms of x for y equals the square root of f of x. All we have to do is take our function f of x and put that under our square root. So our new function y equals the square root, take f of x, which is x minus 2, put it under the square root. Fill in the table of values and sketch and label y equals f of x and y equals the square root of f of x. So first filling in the table of values for y equals x minus 2, which is our f of x function. X equals negative 1, y would be negative 1 minus 2, which is negative 3. X is 0, 0 minus 2 is negative 2. X is 2, 2 minus 2 is 0. 2.5, 2.5 minus 2 is 0.5. X is 4, 4 minus 2 is 2. X is 6, 6 minus 2 is 4. And x is 11, 11 minus 2 is 9. Now let's calculate the square root of f of x. So y equals the square root of x minus 2. Well, x minus 2 are the values that we just calculated in this column. So we're just taking the square root of these numbers. Square root of negative 3. Well, we can't take the square root of a negative number, so that is undefined. Next one is negative 2. Same thing, we can't take the square root of a negative number. It's undefined. What is the square root of 0? You probably know it's 0, but let's bring up our calculator. Second square root 0, we get 0. Square root of 0.5, second square root 0.5 is 0.7071, etc. Square root of 2, 1.4142, etc. Square root of 4, it's a perfect square, so that's 2. Square root of 9, that's a perfect square, it's 3. Next, let's graph each of our functions, starting with f of x equals x minus 2. When x is negative 1, y is negative 3. When x is 0, y is negative 2. When x is 2, y is 0. When x is 2.5, y is 0.5. When x is 4, y is 2. When x is 6, y is 4. And when x is 11, y is 9. There's our points. We can join them with a line. Next, let's graph our function y equals the square root of x minus 2. For x equals negative 1 and x equals 0, our function y equals square root of x minus 2 is undefined, so we can't plot any points. Our first point would be at x equals 2. Our y value for y equals square root of x minus 2 is 0. And then at 2.5, we have a y value of 0.7, so it's a little bit higher than our other function. And then at 4, it's 1.4, it's about halfway there. And at x equals 6, our y value is 2. And finally, at x equals 11, our y value is 3. So we can join those points to draw the graph of our function y equals the square root of x minus 2. Notice that the graph of this function goes above the graph of the original function, between 2 and 3, and then it's below that after. What happened to the graph of y equals the square root of x minus 2 for values of x which are less than 2? The graph does not exist. For values of x less than 2, because we can't square root a negative number. What are the invariant points? Where will you always find invariant points on y equals the square root of f of x? We know that invariant points are the points where the graphs intersect, so the original function and the new function have the same x and y values at that point. We can see one of them. One of them is x equals 2, y equals 0, because we have y equals 0 for both functions. Let's bring up our graphing calculator and graph these functions, and we can find our third one. We have x minus 2. First I'm going to clear that. X minus 2, enter, and then we have square root of x minus 2. Graph that. I'm going to change my window to standard, zoom, standard, and there we go. Okay, so I'm going to find my intersection points, second trace, number 5. First curve, yes, I'm on the first curve, hit enter. Second curve, it jumped, hit enter, and yes, hit enter. Intersection at 2, 0, and then I want to do that again because we already had that point. Second trace, number 5. This time I want to move my little dot closer to the other intersection point, so I'm going to move it on this side. Okay, so up above, hit enter, it jumps to the other graph. I'm going to move it closer to that intersection point I'm trying to find, hit enter. Do I want to guess? No, hit enter, and it's at 3, 1. So invariant points are 2, 0 and 3, 1. Where are we always going to find invariant points when we take the square root of a function? Well, the square root of 1 is 1 and the square root of 0 is 0. So the invariant points will always occur at y equals 0 and y equals 1 for square root of f of x. This is because the square root of 0 equals 0 and square root of 1 equals 1. State the domain and range for y equals f of x and y equals square root of f of x. So y equals f of x, it's a linear function. Our domain is x such that xer is all values, and our range is the same, y such that yer. For our square rooted function, y equals square root of f of x, our domain x such that, well, we can see from our table of values and also from our graph that it's undefined until 2, because before an x value of 2, the y values are negative for x minus 2, and we can't square root a negative. So we know that our domain for y equals the square root of f of x is x has to be greater than or equal to 2 x e r. Range y such that, again, looking at our table values and our graph, for that first point where x is defined at x equals 2, our y value is 0, and then our y value increases from there. So we know that y has to be greater than or equal to 0, y e r. The graph of y equals 4 minus 2x is given. Complete a table of values and sketch the graph of y equals the square root of 4 minus 2x. Let's plug our x values into our square root function, square root of 4 minus 2x, and calculate the y values for that function. Bringing out my calculator. Square root of 4 minus 2 times negative 6 gives us 4. 0, if we plug 0 in, then it would just be the square root of 4, which is 2. If we put 2 in, then we would have 4 minus 4, so square root of 0, which is 0. And then if we put 8 in, square root of 4 minus 2 times 8 gives us an error because we would get a negative number, so undefined. Next, we can plot these points to graph our square root function. So at x equals negative 6, y is 4. At x equals to 0, y is 2. At x equals to 2, y is 0. We also saw that we always have an invariant point at y when y equals to 0, which we already have, that was x equals 2, y equals 0, and then when y is equal to 1, which is here. And then we can draw our graph. Remember, it's a curve. So it looks something like that. State the coordinates of any invariant points. Well, we just said that our invariant points happen when y equals to 0 and y equals to 1. So how can we find these? Well, algebraically, we can sub y equals 0 and y equals 1 into our function and then solve for x. We could also use our graphing calculator and find the intersection points. Let's do it algebraically this time. Let's sub in y equals 0 because we see that it's here. So we should get x equals 2. So let's give it a try. 0 equals the square root of 4 minus 2x. We need to square both sides to move this, get rid of the square root. 0 squared is still 0. We have 4 minus 2x. Then we want to move our x's to one side and have our non-x's on the other. I'm going to add 2x to both sides. We get 2x equals 4, and then divide by 2. We get x equals 2. And then we can do our second one, y equals to 1. Square root of 4 minus 2x. Again, we need to square both sides. 1 squared is still 1. Next, I'm going to add 2x to both sides. And then I'm going to subtract 1. And then divide by 2. And we get that x equals 1.5. So our invariant points are x equals to 2 and y equals 0 and x equals 1.5, y equals 1. State the domain and range of y equals the square root of 4 minus 2x. Our endpoint is at x equals 2, y equals 0. And if we look at our graph, our graph is heading towards the left, so our x's are getting smaller. So our domain x such that x is less than or equal to 2 xer. And our range is y such that, so our endpoint is 0. We're square rooting, so we get positive numbers. So y such that y is greater than or equal to 0, yer. How can the domain be determined algebraically? We can look at the restrictions on square root of f of x. Which is always that f of x has to be greater than or equal to 0. So restrictions for y equals square root f of x are f of x has to be greater than or equal to 0. In our case, f of x is 4 minus 2x, which has to be greater than or equal to 0. Subtract 4. We get negative 2x is greater than or equal to negative 4. Then we need to divide both sides by negative 2. And remember, when we multiply or divide by a negative times or divide by a negative, we need to switch the inequality sign. So we would get x is less than or equal to negative 4 divided by 2 is positive 2. And then that becomes our domain. Here we have a summary. Y equals the square root of f of x is only defined when f of x is greater than or equal to 0, since we can't take the square root of a negative number. The domain of y equals the square root of f of x consists of values in the domain of f of x where f of x is greater than or equal to 0. So any values that were in the domain of the original function where the y values were positive. The range of y equals the square root of f of x consists of the square roots of the values in the range of f of x where the square root of f of x is defined. Invariant points lie on the lines y equals to 0 and y equals to 1. You can predict the location of y equals the square root of f of x relative to y equals f of x using the values of f of x. Value of f of x. Let's compare this to our graph that we have up above here. Relative location of graph of y equals square root of f of x. So first column here, f of x is less than 0. Well, if f of x is less than 0, then the graph of y equals square root of f of x is undefined, so there is no graph. Then f of x equals to 0. The graphs of y equals the square root of f of x and y equals f of x intersect at y equals 0. So that was this invariant point at x equals 2, y equals 0. Next, when f of x is greater than 0 but less than 1, then the graph of the square root of f of x is above the graph of y equals f of x. So when we do this little curvy part between the two invariant points, that part of the square root of f of x is going to be above the original function. Then when f of x equals 1, just like when f of x equals to 0, the graphs of y equals square root of f of x and y equals f of x intersect. So we have that invariant point there. After that, when f of x is greater than 1, the graph of y equals the square root of f of x is, that should say below, square root of f of x is below the graph of y equals f of x. So we see here the graph of the square root of f of x is below the graph of the original function y equals f of x. Given the graph of y equals g of x below, sketch the graph of y equals the square root of g of x on the same grid. Then write the equation for y equals the square root of g of x in terms of x. So starting with drawing our graph, we know that our invariant points are going to be at y equal to 0 and y equal to 1. So find the points on your graph where y is equal to 0 and y is equal to 1 and put a dot. Then we want to find some other values that we can take the square root of. So we're looking at the y values, taking the square root of those to plot the y value for our new function. The x values will be the same. So for example, if I look at when y is equal to 4 on my original function, it's right there. It's approximately 6.6, something like that. The square root of 4 is 2. So I would just go straight down 2 and put a dot in the same location x value wise, just at 2 instead of 4 for the y value. And then another perfect square is 9. So looking at the y value of 9, it's at x equals to 0. So the square root of 9 is 3. I just go at x equals 0, y equals 3. And those points are going to be on my new function. Remember that when your y values are between 0 and 1, the graph of the square root function is going to be above the graph of the original function, and then after that it's going to be below. So it looks something like this. That is our y equals the square root of g of x. Now we want to figure out the equation for y equals the square root of g of x in terms of x. First of all, we need to figure out the equation for the original function y equals g of x. G of x is a linear function, which the general form of a linear function is mx plus b, where m is our slope and b is our y-intercept. Our y-intercept, we can see, is 9, crosses the y-axis at 9, so b equals 9. We want to figure out our slope of our original function. So in this case, I can see 2 points that are on the line. I have this point here at 8 and 3. And this point here is at 4, 6. So I could use my slope formula, y2 minus y1 divided by x2 minus x1. Or in a situation like this that's really simple, I can count my rise and my run. So it's moving down as it moves to the right, which means it has a negative slope, and it's going to the right 1, 2, 3, 4, and then down 1, 2, 3. So 4 and right 4 and down 3, and we know that it's a negative slope. So then we have g of x equals negative, the rise of the slope is 3, the run is 4x, and then plus the y-intercept, which is 9. Now that we have the equation for our original function g of x, we can then write y equals the square root of g of x, which is the square root of negative 3 over 4x plus 9. Now let's also practice our skills of writing things in transformation form. So let's factor out the negative 3 over 4 from what's under the root so that we can write it as a b value. So 9 divided by negative 3 over 4, because we need to factor out the negative 3 over 4 from the 9, would be 9 divided by bracket negative 3 divide 4, close bracket, gives us negative 12. So then we would get y equals square root negative 3 over 4 bracket x minus 12. So this would represent, the minus 12 would represent a shift 12 units to the right from the original square root of x function. So if we look, our endpoint has been shifted 12 units to the right. So that matches up. Then what if we wanted to write it as, instead of having a b value, we had an a value as well? So we can do that. This is one possible function, y equals the square root of negative 3 over 4 bracket x minus 12. Or we can take out as much of that coefficient as we can and create an a value. Y equals square root. I can split up my fraction because I know that 3 is not a perfect square, but 4 is a perfect square. So I can write it as 1 over 4 positive times negative 3 and then x minus 12. And then I can take out the 1 over 4 because I can take the square root of it. So it becomes y equals square root of 1 over 4 is 1 over 2, and then square root negative 3x minus 12. So that's another option for how we can write the equation of our function y equals the square root of g of x. The graph of y equals the square root of f of x is shown. State the coordinates of any invariant points. So this time we have the square root function. State the coordinates of any invariant points. Well, again, we know that those happen when y is equal to 0 and when y is equal to 1. So just put dots on your graph wherever y is equal to 0 and y is equal to 1, which occur at x equals to negative 4, y equals to 0, and x equals to negative 2, y equals to 1. Part B, sketch the graph of y equals f of x on the same grid and write an equation for y equals f of x in terms of x. So we know that f of x is going to be a linear function. To draw a linear function, all we need is 2 points. We have 2 points. We have the 2 invariant points. So we can use those to plot our, to draw our graph. I can also find other points by looking at the y values of the square root function and squaring those values to get the y values of my new function. So for example, if I look at the point that is at right there, that is 4, 2. If I square the y value, the x value stays the same, but if I square the y value, 2 squared is 4. So I go straight up and I put a point at x equals 4, y equals 4. That point is on the linear function. So I can join my points with a line. And there's my function y equals f of x. So we've sketched it. Now we want to write an equation for y equals f of x in terms of x. It's a linear, so f of x equals mx plus b. Let's find our slope. We have some points on the graph, so we can use any of those. We know that our invariant points, which are on both graphs, are negative 4, 0, and the second point is negative 2, and y equals to 1. Our slope formula, y2 minus y1 over x2 minus x1 becomes, if this is my x1, y1, and then my x2, y2, I'd get y2 is 1 minus y1 is 0. x2 is negative 2 minus x1 negative 4. 1 minus 0 is 1. Negative 2 minus negative 4. That'd be negative 2 plus 4. So that gives me a positive 2. So our slope is 1/2. So f of x equals 1/2 x plus b. Now it looks like we can see our y-intercept. It looks like it's 2, but let's just algebraically double check that. So let's sub a point into this equation and solve for b. It can be any point, so I'm going to pick my negative 4 is 0, so y is 0. 1/2 times negative 4 plus b. Okay, so what do we do here? We sub in a point on the line. Y equals f of x and solve for b. 0 equals 1/2 times negative 4, so that just means negative 4 divided by 2 is negative 2 plus b. Add 2 to both sides. We get b equals 2, which is what it looks like on the graph. So then our function f of x would equal 1/2 x plus 2. And the question's not asking for this, but as a side note, then y equals square root of f of x is y equals square root of 1/2 x plus 2. Compare the domain and range of y equals f of x and y equals square root of f of x. Identify and compare the domain and range of the functions y equals x squared minus 4 and that should say y equals square root of x squared minus 4. Use your knowledge of transformations to graph y equals x squared minus 4. So transformations, this is our k value, negative 4 would be the k value. So that means that this graph would be x squared shifted down 4. Okay, let's draw a sketch of it. So x squared starts at 0, 0. Shift that down 4 units. It would be at 0, negative 4. Then x squared has a point at x equals 1, y equals 1. Shift that down 4 units. It'd be x equals 1, y equals 3. And symmetrical on the left side. So instead of at negative 1, 1, it's going to be at negative 1, negative 3. Then x squared, 2 squared is 4. So we usually have a point at 2, 4. Shifting down 4 units, we're going to have a point at 2, 0. And then symmetrically on the left, a point at negative 2, 0. Another point usually we have on x squared is x equals 3, y equals 9. Now we're going to shift that down 4 units, so x equals 3, y equals 5. And symmetrically on the left, x equals negative 3, y equals 5. Then we can join our points to draw a parabola. Okay, some information about our quadratic minimum value. The minimum value is the y value of the vertex, which in this case is y equals negative 4. The vertex is at 0, negative 4. It opens up the domain of x squared minus 4, the domain of all quadratics, unless it's a word problem, is x such that x is an element of the real numbers. The range of y equals x squared minus 4. For quadratics, the range is always determined by the max or min value. In this case, it's a min value, which means all of our values are greater than or equal to that value. So y such that y is greater than or equal to negative 4, y r. Now we're talking about some information about the square root function, y equals square root x squared minus 4. So let's draw it. We know that invariant points happen when y is equal to 0 and when y is equal to 1. In this graph, we have two different points where y is equal to 0 and two different points where y is equal to 1. So we actually have 4 invariant points for this question because we're no longer looking at square rooting linear functions, we're now looking at square rooting quadratic functions. And then to find another point, looking at the point that we used to graph our original function, we had -3 and 5. So if we take the square root of 5 with our calculator, square root of 5 is 2.23. So square root of 5, our x value stays the same. We're just dropping down from 5 to a y value of 2.23. So about there. And same with on the other side because it's symmetrical. So we're dropping down from a y value of 5 and x equals 3, going straight down to a y value of about 2.2, still x value at 3. And then we can draw our square root function. So this time we're going to have two arms. Okay, so again, when y is between 0 and 1, the graph of the square root is going to be above. And then after that, it is below the original function. So a little bit above, and then after that, it is below our original function. So something like that. We have two arms. This is our y equals x squared minus 4. Y equals square root of x squared minus 4. And this is also y equals square root of x squared minus 4. Both of those pieces together. So domain of y equals the square root function. Well, let's do this algebraically. We can see from the graph that we have x values that are less than or equal to 2. So starting here and going that way. We also see from the graph that we have x values that are greater than or equal to 2. Let's see how we can get this algebraically. Looking at y equals the square root of x squared minus 4, we know that the restrictions are the original function, x squared minus 4, has to be greater than or equal to 0. So let's start solving. We're going to add 4 to both sides. We get x squared has to be greater than or equal to 4. Now we're going to square root, but remember if we're square rooting an unknown value that's squared, we have to do plus minus square root of x squared is greater than or equal to. Normally we would put the plus minus square root here, but that's when we're doing equations, so equal sign. Here we have an inequality, and we recall that when we multiply or divide by a negative in an inequality, we have to switch the sign. So in this particular situation, we need to do it a little bit different. So let's go up here, and we're going to do the positive. So if we have positive, square root x squared is greater than or equal to square root of 4, then we just have x is greater than or equal to 2. Then if we look at the other situation where we have the negative square root of x squared is greater than or equal to the square root of 4, if we square root each side, we get negative x is greater than or equal to 2. But then we have negative x, we want positive x. So we need to divide by -1 or multiply by -1. And that gives us x is less than or equal to -2. Because remember, we divide or multiply by a negative, then switch, inequality sign. So our domain, as we saw in our graph, it includes any value that is less than or equal to -2. It also includes any value that is greater than or equal to +2. So let's write that out. Domain x such that x is less than or equal to -2, and also x is greater than or equal to 2 XER. The function y equals the square root of x squared minus 4 does not exist when x squared minus 4 is less than 0. In this case, it does not exist between x equals -2 and x equals 2, as we saw in our graph. And in our domain, the quadratic function here is below the x-axis, which means the y values are negative. So our square root function is not defined for any negative y values from our original function, which means it's not defined between x equals -2 and x equals +2. Our range of y equals the square root of x squared minus 4. Our range is the same as the original function for any values that are valid in the square root function. So in the original function, our range was all y values that are greater than or equal to -4. When we square root the function, the only y values that are valid for the square root function would be those that are greater than or equal to 0. So y such that y is greater than or equal to 0, YER, close bracket. Little note here, when a quadratic function opens up and has a minimum value less than 0, in this example, which is below the x-axis, so 2 x-intercepts, the square root function will be in two parts, extending left and right of the x-intercepts with a minimum value of 0. So that's just kind of a recap of the situation that we saw here. Analyzing key points. Use the locations of any intercepts, maximums, or minimums to determine the domain and range. So still looking at that same example from the last page, our function is y equals x squared minus 4, and our square root function is y equals the square root of x squared minus 4. Our x-intercepts, if we go back to our last page here, the x-intercepts of the original function, x squared minus 4, we're at x equals -2 and x equals 2. So -2, 0, and 2, 0. The y-intercept of the original function was the same as the vertex, so that was at 0, -4. The maximum value, it didn't have a maximum value, not applicable. And then the minimum value was the y value of the vertex, which is y equals -4. So the domain of y equals x squared minus 4 is XER, all the real numbers. The minimum value of the function is -4, so the range would be y is greater than or equal to -4. Looking at our square root function, our x-intercepts were also at -2 and +2, -2, 0, and 2, 0. Our y-intercept, we did not have a y-intercept for the square root function, so not applicable. Maximum value, the values just keep going up, so also not applicable. And then the minimum value for the square root function, the lowest y value was 0. Since the square root function y equals the square root of x squared minus 4 has x-intercepts of x equals 2 and x equals -2, the domain of the function is x is less than equal to -2 and also x is greater than equal to 2. Since the square root function y equals square root of x squared minus 4 has no y-intercept, the range of the function is y is greater than or equal to 0. Given the graph of y equals f of x, sketch the graph of y equals the square root of f of x on the same grid. Clearly mark all invariant points. Okay, starting with our invariant points, when y is equal to 0, we have x equals 4, negative 4, and x equals 4. And then when y is equal to 1, we have x is negative 3 point something, and x is positive 3 point something. So we have 4 invariant points, again, because we're looking at a quadratic. To get some other points that can help us to graph, we can, again, take the square root of some values. So up here, our vertex is at 0, 8. We can take the square root of 8. Square root 8 is 2.82. So dropping straight down from 0.8 to 0 and about 2.8 would be about there. And then we could do the same for this point here is at 2, 6. We can take the square root of 6, which gives us about 2.4. So dropping down from 2.6 to 2 and about 2.4. And that would be symmetrical on the other side. So at negative 2, 6, taking the square root would put us at negative 2 and 2.4. I'm going to change the square root function points to purple so we can see the difference better. So joining our points, remember that between the y value of 0 and y value of 1, our function is going to be above the original function. And then it's going to be below for all other values. And then we get back to being between our invariant points. So again, it's going to be above. So something like this is our function y equals the square root of f of x. So we've done what the question asked, but let's also find an equation for the square root of f of x, which means we need to find an equation for f of x. It's a quadratic. I know the vertex. I'm going to use vertex form, ax minus h squared plus k. F of x equals, we don't know the a value, x, we know the vertex is 0, so minus 0 squared, and then 8 plus 8. I don't actually need to write this minus 0, so that's just going to be x squared. I'm now going to sub in another point, so I have the point 2,6 or negative 2,6 or the x-intercepts 4, 0 and negative 4, 0. I can sub in any one of those points. I'm going to go with the point 2,6. So y equals 6. X is 2 squared plus 8. I want to isolate the a, subtracting 8. Negative 2 equals a. 2 squared is 4. Then I want to divide by 4. I get negative 1/2 equals a. So then our function is f of x equals negative 1/2 x squared plus 8. I don't need those brackets around the x, but either way. Then the equation for y equals square root of f of x is square root of f of x equals square root of negative 1/2 x squared plus 8. And we can divide out the negative 1/2. We get square root of f of x equals square root negative 1/2 bracket x squared. Then use our calculator. 8 divided by negative 1/2 is negative 16. So x squared minus 16 in brackets. When you have a quadratic function that opens down and has a maximum value greater than 0, this will mean it's above the x-axis, so you have two x-intercepts. Then the square root function will be between the two x-intercepts and have a maximum value equal to the square root of the original maximum value. Graph the functions y equals 2x squared plus 3 and y equals the square root of 2x squared plus 3 on the grid. Y equals 2x squared plus 3, it's a quadratic. It has a y-intercept at 3, so I can plot that point. Then I can plug in some numbers. If I put in 1 for x, I get 2 times 1 squared. 1 squared is just 1, so 2 times 1 is 2, plus 3 is 5. So when x equals 1, y equals 5. And then if I put in negative 1 squared is positive 1, 2 times 1 is 2, plus 3, so we get when x is negative 1, y is 5. So here's the original quadratic. Then graph y equals square root of 2x squared plus 3. Let's take the square root of our y values. Square root of 3 is 1.73, so about there. Square root of 5 is 2.23, so dropping down from this point down to about here, 2.23. And symmetrical on the other side. And we could calculate a few more values for this one. The square root of 2 times 2 squared plus 3 is 3.3. So when x is 2, y is 3.3. And it's symmetrical about the y-axis. So when x is negative 2, y is 3.3. We can join our points together. That's the graph of y equals the square root of 2x squared plus 3. And the first one was our graph of y equals 2x squared plus 3. State the domain and range of each function. Domain of y equals 2x squared plus 3. It's a quadratic, so the domain is x such that x is an element of the real numbers. And the range of y equals 2x squared plus 3 is defined by the fact that it's opening up and it has a minimum value at 3. So y such that y is greater than or equal to 3 and y is an element of the real numbers. Then the domain of y equals the square root of x squared plus 3. The graph just looks like a much wider parabola, so it's still x such that XER for the domain. And the range of y equals square root of x squared plus 3. To get our y values for the graph of y equals the square root of 2x squared plus 3, we took the square roots of the y values on y equals 2x squared plus 3. So our minimum value on the square root function is the square root of the minimum value on the quadratic function, which was a y value of 3. So the range is y such that y is greater than or equal to the square root of 3, and y is an element of the real numbers. When you have a quadratic function that opens up and has a minimum value greater than 0, which means above the x-axis, so there would be no x-intercepts, the square root function will be a wider version of your original graph and will have a minimum value equal to the square root of the original minimum value. That brings us to the end of Chapter 2, Lesson 2.